Welcome, everyone. Thank you so much for being here today and for being part of this week and making this amazing experience happen. We are Team Explorer, and we're going to be presenting the Parched mission, which is aptly named because we're studying the loss of volatiles, and especially water, in the inner solar system. Parched stands for the planetary atmospheres and reservoirs, compositional history, and escape dynamics. And this is our team. So I know you're really all here for the cool engineering, but I come from a science background, so the science justification is the part that really excites me, and that's what I'm going to start with here. So when the solar system first forms and condenses from the nebular gas, the temperature gradients in the disk cause the material that forms the solids to actually also have a compositional gradient. Closer to the sun, as we can see in the top left, the material is mostly rocky, whereas far from the sun, due to the colder temperatures, ices can condense, and we have wet material. This is all really cool, except for the fact that we're in the inner solar system right now, and all things considered, the planet's pretty wet. So clearly at some point, water had to traverse that line and come into the inner solar system. The debate about how this occurred is still very much active, but one of the key lines of evidence that people use is the hydrogen to deuterium ratio, which we can think of as the fingerprint of water in different parts of the solar system. We can see this in the bottom left plot here. You don't really need to read the plot, but just note the scatter. There's a lot of different signals of these across the solar system. The Earth plots on that blue line in the middle, and you can notice in the light green, carbonaceous chondrites are the most similar to the Earth. And if you look at the first red dot, just not too close but not too far from the Earth, is Halley's Comet, which is a similar type comet or the exact type comet to the one that we will be looking at. But that's getting a little bit ahead. This plot on the right, you also don't need to really understand, but the takeaway is that when the Earth is forming, we consider it to come from two main reservoirs of material, wet and dry. The wet material, oftentimes scientists just approximate as all carbonaceous chondrites because they plot so well on the D to H ratios. However, as you can see in these other plots, the blue scatter is the carbonaceous chondrites, and you can see, for instance, in the top right, where the primitive mantle plots, this doesn't work for all of the other species. So in order to fully figure out both the exact ratio of wet and dry that we need when we're forming the planet, as well as the right mix of different wet bodies, we need both much stronger measurements of how volatile elements, of the composition of different water and volatile elements in the system, as well as how these elements actually escape from the bodies when they enter the inner solar system. And that brings us to the Parched mission. So our goal is to determine whether solar-driven processes can explain both the acquisition and the loss of volatile material in the inner system. And to do this, we're going to look at two things: the release of volatiles from primitive bodies and the long-term escape of volatile species from terrestrial planetary atmospheres. To do this, we're studying two components, a source and a sink. And here we have our mission assessment matrix, which determines how well our objectives correlate with the NASA Decadal Survey. I'm not going to spend too much time on this, but I do want to highlight that we are covering almost all of the inner solar system objectives, as well as just under half the total science priorities. So, why comets? Why are these our source for volatiles in this mission? It's because comets formed over 4.5 billion years ago, and they haven't had a lot happen to them since. When they come into their brief perihelion passage, they are exposed to the sun, and their rich volatile interiors are outgassed, but otherwise they're relatively unaltered in the outer solar system, so their reservoirs are primordial. They also formed outside the snow line, obviously because they have ice, but their really eccentric orbits cause them to come in very close to the sun and the inner solar system planets, which makes them a viable option for delivering volatiles to the inner solar system planets during formation. Why Venus? Venus, because the Earth and Venus are sister planets. Earth and Venus form at almost the same heliocentric distance, they're almost the same size in terms of exoplanets and other systems we see, and they could not possibly look more different from one another today. Earth is a nice balmy temperature that we can all live on. Venus is over 460 degrees C and has over 90 times the atmospheric pressure that Earth does. How did this happen? studying Venus will allow us to consider why Earth is habitable today, as well as understand the temporal and temporal variation in evolution of the planet. Also, kind of uniquely, Venus does not have an magnetic field, so it's unprotected from the solar wind. This allows it to be exposed to atmospheric loss rates that are very, very high, because not only is it a little bit closer, but it doesn't have the wonderful magnetic sheath that the Earth has to protect us from the solar wind. This leads us to our two objectives. Our objective 1 is to determine how solar heating and solar wind forcing modify the volatile release, plasma environment, and morphological properties of our comet. And objective 2 is to determine whether changes in solar wind conditions produce measurable changes in the flux, composition, and energy of atmospheric escape at Venus. And that takes us all the way finally to our specific comet, P2005 T4 Swan. It was first discovered in 2005 when it last orbited around the sun, and this is one of the only existing photos of the comet at that time. And it's kind of hard to see, especially on this projector. But give it a good look. You see the comet? Because I definitely don't see the comet. We think it's right there, and this is just one extra little plug for why this comet needs to be explored. This was here for multiple months. It was visible, but just barely. And even after it had been discovered, there's still hardly any pictures left from that time. So there's a lot left for us to do if we want to learn more about this comet. Based on the trajectory of the comet, we identified 2 different times when we could possibly actually fly by this comet. And this video I will play again as well. You can see the comet is the green flying in there, and right when it hits that red triangle, and then right when it hits our blue triangle here, these are the 2 points that, due to its very inclined and also retrograde orbit, we think that we can actually reach flyby. And it's when it actually passes through the solar system's inclination plane. With that, we call these the cold and the hot flyby cases. In the hot flyby case, we're 0.7 AU to the sun, and because of this, we have a really strong solar wind, which is going to cause very strong water sublimation, a big bright coma, lots of outgassing, really high signal-to-noise ratios for our ion and volatile imaging, and just a lot of really, really great data. This is a great option. Our much further away case, the cold case, is 4 AU to the sun. So much, much weaker solar wind, which is decaying at 1 over the radius squared. And because of that, we're going to have very weak outgassing, very weak comas and ionizations. However, we are going to have up to 100 times deeper plasma penetration into the coma. And the reason for this is because there's not that volatile outgassing, we're actually not going to have a protective barrier for this comet that's blocking what limited solar wind there is there from penetrating into the coma. So this would allow us to actually see what this plasma generation initially looks like at the beginning of the coma's pass through to the sun and on its way out, and potentially better characterize how this plasma actually interacts with the comet's nucleus and coma deep down within. These are 2 simulations I've done for our pass to the comet, given a 1 kilometer comet nucleus and a 500 kilometer away respective location. This also takes into account the solar system location and the solar cycle at the time of our flybys. And as you can see in the hot flyby case on the left, we have a very, very strong coma, very strong tail. Ion tail and dust tail. And on the right, in our cold flyby case, it's much weaker. You can still see some coma forming, but actually if you look closely, you can see the dark, you can't really tell on the slide, but it's much darker blue out here than it is around there, and that's because in our hot flyby case, the coma is so large that we're actually completely seeing a little bit of it the whole time. So we have really, really different situations here. And again, as I mentioned, that's because there's no bow shock in the cold comet case, which is just, if you don't like my simulations, you can see a little bit clearer in the cartoons here. Just to make matters a little bit worse, I'll leave that up for another second. Just to make matters a little bit worse in terms of trying to pick between these 2 options, the cold flyby case additionally has much, much more science time. It has 3 times as much science time based on the flyby speed. And trajectory, we'll go into this a little bit more later, but essentially at the 0.7 AU flyby, we will fly by at approximately 77 kilometers per second, whereas at the 4 AU spot, we fly by at 25 kilometers per second. With these really high speeds, these extra seconds could make a really big difference in how much data we're actually able to collect. And that brings us finally to Venus. What you can see here is what Venus would look like if it had a magnetic field and a normal ionosphere reaction to the solar wind on the left. On the right, this is done with data actually derived from Venus Express, but you can see it almost looks more like a comet. And that's because there's no magnetic field. So its atmospheric escape is much higher. Its ionosphere is being ripped through by this solar wind. And ideally, to really characterize this, we'd like to get measurements all over the place. We'd want to measure the upstream solar wind before it penetrated the planet at all. We'd want to get right at that interaction between the ionosphere and the solar wind. We'd want to get this plasma as it wraps around the planet at the poles, and we'd want to get the atmospheric escape. But again, just like our last comet case, can't really get all of these measurements at the same time unless you're in 2 places at once, which, you know. But what if we could be in 2 places at once? When I was going through this problem with my team of engineers here, they were all really sympathetic with me. I think because they thought I was really struggling and going to have a hard time getting through all of this with all of these decisions. But as a scientist, I decided I did not want to compromise, so I made all of the engineers suffer instead, and I'm now going to turn it over to them, and they'll tell you just how much they suffered.
Thank you. Yes, there was a little bit of suffering involved, but this was a great place to start. Having science's dream mission is always a great place to start, and then we could try and build some reality into it, some engineering into it to make it into a reality. So we started with our mission architecture. We did some exploration of different architectures to figure out which one would be most optimal for science as well as feasibility. We focused a lot on realism for our mission, making sure to use as many flight heritage components and looking into some preliminary analysis of 5 different architectures using 16 separate design points that we figured would be used to differentiate major mission architectures from each other, with one being selected. We started off with figuring out options for 16 different decisions we'd have to make for an architecture. I won't go into all of them, but some ones to highlight include our launch vehicle, the number of spacecraft we use, the number of stages they might have, their propulsion type, if they do any refueling, as well as some more standard things like power source, attitude control, comm architecture, as well as some of our entry orbits in comet proximity. We started off with all of these options, including some less feasible ones, and then we started breaking it down based off of what we knew and could figure out very quickly. Science helped us figure out that some of our longer comet times and larger proximities weren't very feasible for their science, so that helped us take those out. We also found out that excessively staging our spacecraft and having too many spacecraft would make it very difficult for almost any of our launch vehicle options for the orbits that we found. We also found that refueling at the comet wasn't really a good idea, as well as solar panels were our best design choice here for pretty much any architecture. We also removed the SLS and the Long March 9 from our launch vehicles due to political and scarcity restrictions. From there, we developed 5 different architectures, that being our fast, slow, hybrid, big, and dual architectures, and we did some preliminary analysis on each of them so that we knew that we could go forward with the best design that we could come up with. The first one, our fast option, was pretty much your standard chemical propulsion method, where we did a 1-stage chemical burn, a 1-stage spacecraft, 1 spacecraft chemical burn through the ascending node, and then to Venus, basically try and get all the science done as quickly as possible. It would just be like a run and gun mission, getting kind of shotgun blasting as much science as we could. Then we looked at, but it's kind of imprecise, so we'd be further away from the comet and we wouldn't have as long to monitor Venus. Then we looked at the slow option, which is basically a fully electric propulsion option, where we get to see more, see better, but it takes a lot longer for the entire mission to go through. Then we had a hybrid mission, which had a 2-stage spacecraft, which used electric to get to the comet and then to Venus, but then a chemical burn to actually get us into orbit, which sped things up, but ended up being fairly high mass without too much of an additional science over the over like the electric. We then did the big architecture inspired by different Martian mission concepts of utilizing Starship to get all the way there. This one was more for fun, where we figured out if we could just use one big Starship and then refuel a bunch in LEO, we just send the whole thing with all the science we could ever want. But that's pretty impractical for cost. So that one we didn't really go with. We then humored science and did the dual architecture, where we utilized 2 spacecraft to hit both nodes, utilizing a hybrid propulsion system, the same as the hybrid before, this time with 2 different spacecraft trying to fit onto one launch vehicle. We judged these based off of their scientific return, feasibility, and robustness, and actually found that the scientist's dream was also pretty close to the engineer's dream. It had the maximum scientific return because it was science that we have pretty much never seen before. We're seeing a comet both before and after a sun flyby, seeing it, as science mentioned, both with high solar wind and low solar wind, more penetration. We get a bunch of different science from the two. And then, if designed right, they can both return to Venus and perform simultaneous measurements, pretty much generating double the scientific output as any other mission architecture that we looked at. We also saw that it was feasible with a Falcon Heavy, with a C3 of around 64 meters squared per second squared that we calculated from trajectory we'll mention in a little bit. That is, we will also prove that we will be able to hit this mass limit of around 3,600 kilograms. And then robustness was also a huge hit for this option, because each individual spacecraft would be able to complete all level 1 science requirements as well as additional level 2 science requirements, even if the other spacecraft were to fail. So it's just a huge bonus to be able to do both, and it also provides redundancy in the fact of an entire additional spacecraft, let alone redundancy within each spacecraft. So I'd like to present to you the con ops for Parched. Basically, how I described the kind of the 2 spacecraft hybrid architecture, they will both launch from Earth in the December of 2030. They will stay together for a 5-month commissioning period until, I believe that's 2031 July. Then they will separate, and as they go through their first Earth flyby, you'll see the inner spacecraft will immediately head towards the ascending node for 2034 February, and then go into a burn for Venus, with a chemical stage specifically to insert itself into the orbit, while the outer spacecraft continues on a much longer travel path to a 2035 descending node flyby before returning to Venus. These will then go into mirrored polar orbits around Venus, and will be mirrored such that while one of them is in the Venus atmosphere, the other one is in the atmosphere, the other one's outside the atmosphere, so we can provide simultaneous science of measurements of the solar wind and Venus atmosphere to see how they interact over our entire monitoring period. So, without further ado, I'd like to introduce you to Snoopy and Woodstock. Snoopy is the larger of the duo. It's designed to take the longer, treacherous path out to the descending node of our comet before meeting up with Woodstock at Venus, and then they will perform dual measurements. Woodstock is smaller and will basically go directly to Venus from its ascending node flyby, and will actually be able to complete the entire level 1 science objectives before Snoopy even arrives. But Snoopy is also capable of achieving all of our science objectives if Woodstock were to suffer a failure. Now I'll hand it off to Trajectory to show how all of this is possible.
Okay, so let's move on to astrodynamics. So based on this requirements, there are a couple of key requirements we need to secure. First one is the 2 spacecraft needs to be launched in a single launch vehicle. So the first arc usually going to be almost the same. Second constraint is obviously one needs to go to the ascending node, and then the other needs to go to descending node. Finally, both spacecraft needs to get back to Venus, and then get into an orbiter situation. So this is a very highly constrained problem, and then we did a lot of trade analysis and then broad search on this, and we finally found a solution. So it launched the end of 2030 December, and then make flyby at 2034 and 2035 respectively, and then having 5 flybys for each, it arrives at the Venus successfully in 2037 and 2039. The total delta V, this is first order approximation based on the impulsive control assumption with very small grid you can allow based on a Lambert arc patching. And then Snoopy yields which is going to the descending node. I will maybe play once more. with less than like 1 kilometer with like 5 flybys. And then like the Woodstock, which is going to the inner one, which is the yellow one, takes like 5.16 kilometer. So that is like the interplanetary trajectory situation. So let's say we arrived at Venus, and now we would like to do some actual science out there. The important part is like to trade the orbit stability and also like the effectiveness of the science. And after some discussion, we landed on this like nominal science configuration of like one going like the north polar elliptic orbit and then the south elliptic orbit, which roughly periapsis is like 160 to 200, and then apoapsis is like roughly like 60K kilometer, which orbit period is like roughly less than like one day basically. And note that like the Woodstock arriving at the Venus 2037, so it's a little bit earlier, 2 years earlier than Snoopy, which arrives at like 2039. Even like one Woodstock 2 years can like achieve the minimum science requirements, while if it survives 2 years, which we are shielding enough, Snoopy arrives at like in like 2039, and then this is going to be the first dual mission around the Venus. So like the science return is going to be even boosted. So the tricky question is like we will not be able to reach this like science orbit like immediately after. The reason being is like this is like a little bit too small, and the energy is like too constrained compared to the flyby insertion, which has like a delta V infinity of roughly 4 kilometers to 4.5 kilometers. So we introduced some like a unique combined chemical and electric propulsion based orbit insertion, where you first burn the chemical impulsive burn at the periapsis when you come to the Venus proximity, which is then captured to this like red orbit, which is like much bigger than the actual science orbit, and then spend like a month or two to reduce the apoapsis using the EP. This like unique combination enables like the overall interplanetary to the orbit insertion to the like settlement to the science orbit. Yep.
Thank you. And with that, because our talented trajectory and mission architecture teams have been able to give us an orbit, the science team, a mission where we're able to actually hit multiple orbits with both the comet and Venus. I present to you the scientific requirements that we are fulfilling, and I will be talking about the scientific equipment that will help fulfill these requirements. So broadly speaking, the first two requirements are about going around our comet T4. The next two requirements are about going around Venus. And the last requirement, just by virtue of our orbit, will help of our trajectory, will be to look at the space dust and plasma environment in the inner solar system. And to quickly go around the requirements, we're doing a flyby of T4. And firstly, we're looking at the gross morphology, which was one of the requirements of the space challenge. We don't know what the nucleus looks like. As Jack showed you in a picture before at the beginning, it's a very faint object. The nucleus might very well be fragmented, so that's one of the mission requirements to look at. Once we've done that, we would like to get close to the comet and see what its local dust and plasma environment look like. This is especially important at the ascending node because we're much closer to the sun and we're going to get much more interaction with the solar wind. But it's equally important at the descending node because now the comet has been through its perihelion and we're able to see how it has changed through its flyby close to the sun. Simultaneously, Venus presents an opportunity to look at its interaction with the solar wind, especially considering the fact that the solar cycle will be peaking somewhere around 2035 to 2036. Estimates on that vary a lot depending on who you look at, but that will allow us to do a multi-year observation around Venus's orbit, going all the way down to about 160 kilometers and going all the way up to 60,000 kilometers. The science equipment that allows us to do these measurements has been designed taking into account the advantage that this trajectory gives us. So, for example, because we're able to go both to the ascending and the descending node, we are trying to take advantage of the fact that there are some measurements that have to take place very fast and some measurements that have to take place very quickly in terms of both the plasma as well as imaging. And at the same time, we're also trying to optimize for the fact that we have to do these same measurements at Venus. And luckily, the instruments that we're using at the comet will be the same instruments that are used at Venus to take the same kinds of measurements. Because And we also made sure to not be grounded, or we made sure to be grounded for the scientific equipment because we're doing such a interesting trajectory. And so we made sure to take these equipment from previous missions, and all of the equipment that I'm showing here for imaging and spectrometry and for the plasma detection on the next slide have heritage in previous missions such as the Rosetta, Mars Maven, and Venus Express. So just to quickly take you through the instruments, we're using the wide angle and the narrow angle cameras first to look at the comet's gross morphology, which was the first scientific requirement. As you all know by now, it's going to be a very fast flyby of the comet at the ascending node, which means it's at 80 kilometers a second. It's a very challenging image to take of a comet that might be less than a kilometer in size. And we are solving this by not having to rotate the spacecraft, but by using a mirror outside, just in front of the camera. And it's just the mirror that rotates. I will let our GNC expert, Alan, talk more about it later. But with that, we don't have to worry about rotating the entire spacecraft. And the resolution of these cameras, from these heritage missions, is enough with a 500-kilometer flyby of the comet to see even a sub-kilometer comet. Because the comet is going to be obscured by its dust and plasma, we're also taking advantage of infrared and ultraviolet imaging spectrometers, which will allow us to see through the dust. And finally, the mass spectrometers are super helpful around Venus because it'll help us characterize escaping ions due to the interaction with the solar wind. So that was specifically imaging and spectrometry. And in terms of the plasma, again, around the comet as well as around Venus, we're having to look at the magnetic field, ions, electrons, using the ion electron sensor, ion composition analysis, ICA tool, a mutual impedance probe, and a Langmuir probe, which will, again, allow us to look at both around the comet and around Venus.
Now we'd like to bring our subsystem experts over to talk about their subsystems. You can point with that.
Okay, let's talk about some more engineering details of our subsystem. We will start from the communication subsystem. We are aware that even the most destructive science experiments are useless if we are not able to communicate with the Earth. So we decided to make many trade-off analysis, and finally we landed on this configuration, which is based on the heritage of successful missions like Juno and Venus Express. We have two transponders which are both able to operate in both S-band and X-band simultaneously and are used in cold redundancy. Then we have a couple of traveling wave tube amplifier for both band, also in cold redundancy, and a radio frequency distribution unit is in charge of carrying the signal to our set of antenna. We choose to employ a Cassegrain high-gain antenna, which has a main reflector with a diameter of 2 meters, and a medium-gain antenna, which is a choked horn, which can ensure a gain of more or less 18 decibel, and a pair of low-gain antenna, which are helix spiral kind, and we will place them on fore and aft of the spacecraft. They have a wider lobe, so we'll ensure to cover the vast majority of the sky, and will ensure to operate even if we lose control. We choose to follow this path because our spacecraft, especially the Snoopy one, will operate at 4 astronomical units when we will do the flyby with the descending node. So during the analysis, we conducted also many link budget analysis, and we tried to be very conservative. You can see this is our worst case scenario, where we kept a margin of 6 dB and still managed to achieve 8 kilobits per second for our Snoopy spacecraft at 4 AU in X-band with our high-gain antenna. But the operational link budget show that we can achieve 30 kilobits per second if we consider a margin of 3 dB, and we crank up the power up to the maximum allowed by our amplifier. This means that we can achieve, when orbiting Venus, up to 100 of kilobits per second, basically rendering really possible to transmit the high amount of data that we will collect. We have a constraint because we are choosing to use electric propulsion, so we have to manage very carefully our consumption, but luckily our propulsion group made a great job of defining for each leg of the mission how long our thruster need to be fired. So we can see that for each leg of the mission we have plenty of time to do communication without overlapping with the thrust firing. There is only a small problem when we enter Venus with our Woodstock spacecraft, but it's not a real problem because during the orbit insertion we still have both X-band and S-band which can operate at low power without using the amplifier at full extent and still be able to communicate to the Earth thanks to our oversized communications subsystem. We also estimated how much data we will collect. We will do a compression thanks to the FPGA on board of our scientific instrument. So we can see that we can complete the download of the data from our flyby in less than 200 days, even starting from the 4 astronomical unit distance. And this allows us to keep our data in safe. This is the architecture of our command and data handling subsystem instead. Even here we have a good redundancy because we choose to employ 2 onboard computer in redundancy and 1 FPGA that act as a fault control system that take control of the spacecraft in case both of the onboard computer will fault. Then we have this kind of structure where our scientific instrument can directly access the system memory to avoid bottleneck offered by the onboard computer.
As for our guidance, navigation, and control system, our GNC system is very similar in structure to other interplanetary missions. We use 4 reaction wheels and then 8 attitude control thrusters for attitude pointing, as well as momentum dumping of those reaction wheels. We use star trackers for attitude determination, as well as IMUs and coarse sun sensors. Based on the hardware that we have found and the uncertainty estimates given by those hardware, we estimate that we can get a 0.03 degree pointing accuracy during the mission. Now, there are 2 unique aspects to our guidance, our GNC system. The first is during the comet flyby, there's a very high flyby rate. And so the spacecraft will need to determine its own position relative to that comet without any ground input. We chose to use optical navigation, which, as mentioned earlier, has been proven successful using the deep impacts on the Deep Impact mission. And this picture kind of shows how optical navigation works. The other more unique thing about our GNC system is because of the high rotation or the high flyby speed with the comet, it is very difficult to rotate the spacecraft to constantly pointing the measurements at, or the sensors at the comet. So we chose instead to add a scanning mirror in front of our narrow angle camera. This scanning mirror was able to rotate with a motor, and the mirror, we estimate, has a rotation rate of 30 degrees per second. We don't believe that it will need to use, we think it'll be closer to 15 degrees per second, but that gives us a little bit extra margin. And this scanning mirror will allow us to increase the visual time with the comet and allows us to not have to design the attitude control system to be able to slew as quickly. This use of a scanning mirror has been done on the Stardust mission, so it has been proven successful.
All right, for our propulsion system, we chose a hybrid system using both chemical propulsion and electric propulsion. This was chosen because the objectives laid out by trajectory and by science could not be achieved with just a conventional system. So the requirements that we needed for our thrust system was the ability to have a high impulse maneuver, we needed reliability, we needed a high payload mass, and then finally, continuous maneuvering was important for us. So biprop thrusters really excel at high impulse and reliability. There's no guesswork with them really, they've been around for a very long time. And then of course electric propulsion enables very high dry mass ratios, which we needed to fit 2 satellites onto 1 bus. The graph on the right there just shows some of the considerations we had to think about when choosing our thrusters. You know, on paper, you can get a very, very high dry mass ratio at 4,000 seconds of ISP, but in reality, it takes 5 years, and so maybe it's better just to use chemical in that situation. As for the chemical propulsion system, we decided to use MMH and MON3 as our chemical mixture. This was chosen because it was heritage. It was used on the Venus Express mission. And for our main engine, we use an Ariane Group biprop thruster, which comes in at 400 newtons, and it has a relatively high specific impulse for chemical propulsion systems. Leveraging that biprop system, we also used RCS thrusters, which are unconventionally also bipropellant. We chose that because it saves weight to be able to just integrate it with the existing biprop system, rather than having to implement a third cold gas system for our RCS thrusters. And these are just some of the numbers of what was required of our chemical propulsion system. As you can see, our Venus orbit insertion is about 1 kilometer a second, which is nothing too extreme, but I want you to focus on that burn time, which is, you know, it's on the order of hours, not too long, not too short. The mass is also relatively reasonable, but it's important to make a distinction here. Woodstock and Snoopy do have slightly different masses for their propellant, and so they do also have different takes accordingly. For the electric propulsion, we decided to use a NEC gridded ion thruster. Like the biprop engines, they're heritage, they're reliable, they've been used, these specifically on the DART mission. Important metrics to point out with the NEC thruster is the very high ISP, and we have a very wide throttle range for our power. Because our trajectory goes very far away and then very close, we have not always a lot of power and sometimes too much power. So being able to leverage that and get good performance was an important thing for us. Additionally, gridded ion thrusters have very long burn times, and that means you can make little adjustments as you approach the comet. This means that we can get better scientific data, and we're able to make last-minute changes if things aren't exactly where they need to be. Beyond this, we use a 2-thruster redundancy system. That's typical for most NASA electric propulsion systems, but we really only need 1 for operation. And in fact, as you can see with the lifetime there, they can run for very, very long amounts of time. And so, yeah, just being able to have 2 is good. Finally, we have a neutralizer cathode. Spacecraft do have a charge buildup whenever you use any electric propulsion system, and so having that neutralizer cathode is necessary to make sure you don't fry your electronics and you can get good data. Diving a little bit more into what was required for this, what really stands out with this graph is the very high delta V required for Woodstock. 5.7 kilometers a second of delta V is almost not practical for a chemical propulsion system. This is an instance where only EP can really be used to complete the maneuver. And what's even more impressive is the fact that at 245 kilograms, that's half the mass of the chemical propellant needed for the Venus insertion orbit. Also important is the burn time. We are within the burn time margins or within the lifetime margins of the thruster, which is good. You're not going to fry your thruster in orbit. And finally, the graph on the left just demonstrates how we got reasonable performance metrics. Of course, power changes over time, and so your ISP and thrust also changes. So we created this graph that just shows the ISP versus time and did a time average for that and thrust to get some good metrics.
The power subsystem has 3 key roles. Those are generating power, storing power, and distributing power. So we first had to determine what our power requirements were, and we determined that due to the electric propulsion system, we need to be generating a lot of power whenever we are using it. We have our most limiting power cases when we're furthest from the sun. For Snoopy, that's at 4 AU, and for Woodstock, that's at 2 AU. And we then just sized the solar panels accordingly in order to make sure we could generate enough power to maintain all of our operations, still collect data at the Comet for Snoopy, and still be running our electric propulsion system. And then on the power storage side, we need to make sure we can still operate during eclipse at Venus. And then on the power distribution side, we'll utilize a peak power tracking system to make sure the solar variation from 4 AU to 0.75 AU at Venus, we can still operate nominally.
All right, for our thermal control, we are taking advantage of lots of heritage components here. Obviously, we're implementing some MLI, as well as louvers and a heat pipe system to route flux away from those extra sensitive components. In order to size these thermal regulation components, we did a steady state 1D thermal analysis on the coldest case and the hottest case that we would expect Snoopy and Woodstock to see, and able to select a louver size and radiative emissivity, that would allow us to keep our spacecraft at a happy temperature of between -20 and +20 C. The key with this requirement here is that we must make sure that our louvers are facing away from the sun before, for them to provide efficient thermal control of our spacecraft.
Sorry. Now, with our structure, the main purpose of the structure is to protect and house the scientific and other equipment needed to perform our science mission. So we took a lot of inspiration from the Venus Express for the general structure of our vehicles. In general, we have paneling. We're using aluminum for both a film outer layers as well as a honeycomb structure in the middle, and then an additional aluminum skeleton support. We have several mechanisms that support all of our different subsystems. Two of which I will touch on right now are the rotating mirror for the narrow angle camera we've talked about a few times, as well as some release bolts that allow the actual detachment of Snoopy and Woodstock together. They are attached to each other during launch, and then once they're actually out, they will separate from each other and go about their trajectories. And then finally, we have 3 telescoping booms for our science instrumentation. We're using the ones that were used on the Europa Clipper. They were demonstrated to work at 8.5 meters. We will only use them at 5 meters, and this will really improve the data we can gather. Talking a bit about our mass budget. On the high level, Snoopy and Woodstock are both within a 9.91% margin, which is great for us. That's what we want to see. We took into account the wet mass, both the electric and chemical propellant masses, as well as the dry mass in this calculation. Now, beyond just that about 10% margin, we also took margins within each subsystem itself. This was incredibly helpful for us as we were going through this very iterative design process. We started with all subsystems having a margin of 25%. Then as designs iterated and we took more heritage parts and we understood more about these parts and had more confidence in them, we were able to decrease that margin. And you can see a few points here where there are different colors for Snoopy and Woodstock. For the chemical propulsion, electric propulsion, and power, all of these just are slightly different numbers based off the different trajectories and environments that these 2 spacecraft go under.
Okay, I would like to go with the risk analysis briefly given the time constraint. So we followed the standard NASA risk management system, and we divided our risk analysis into 3 components: launch and general mission phase, then the comet flyby, and the Venus phase. So with the launch phase, the main risk was that we have only one window for launching our mission when it can go to both ascending and descending node. But the good news is we have like backup launch windows in 2032 when we can launch like both spacecraft to the ascending node, and it will still be able to fulfill all our requirements. Then we have risk associated with maneuvers and data loss. So for this, we have taken enough margin in our system design. We have 10% margin on the propellant mass, and then we have a lot of data storage capacity, which is more than what is required for our mission. For the comet flyby, since we don't have a lot of information about the comet, that puts us at a great risk of missing the flyby. So for this, since we are using 2 spacecraft and the Woodstock will be flying before Snoopy, it provides us with a lot of information which can be used for a successful Snoopy flyby. Then we have risk of damage to the instruments from the dust particles. For that, from the heritage missions, we have that enough shielding and protective covers basically leads to a successful mission. And then we have another risk that is associated with solar power loss during the comet flyby from the dust and coating. And since we have designed our mission considering that it will be going to comet and then coming back to Venus, we have enough power margins for that. And briefly for the Venus phase, we have risk associated with orbital decay and the thermal management system. So we have considered enough margin for the fuels and the thermal capacity. And a brief cost analysis. This shows all the hardware equipment that we are considering in our system. Most of them is coming from the payload and science instruments. And then we consider all the costs that will be associated with the integration and assembly, system level testing, launch, mission operations. And including all of this, the mission cost is around $1.3 billion, which is quite reasonable for a 2 spacecraft mission that goes to both Venus and Comet. And with this, we would like to conclude our presentation. We are able to accomplish both our goals, flyby measurement for the Comet and the in situ and remote measurements around Venus, while having a lot of information about both the places. Thank you.